This talk is entitled From the Babylonians to Dr Spock and Rogue AI, the past, present and future of technology and the web. So the first section is called Before the Web. This is a brief tech history. Bear with me because some of this will point the future out to you in ways that you may not normally expect. So if we're going to look at the chronology of the digital future, we can go back as far as 1067 BC. That was when the Babylonian king's chief scholar wrote a diagnostic handbook. It was effectively the first little book of logic. In other words, he could say, if there's something wrong with your leg, then try these things out, wrap it in a bandage, see if it's going green, etc., etc. Logic wasn't really formalised though until Aristotle, around 384 BC. And it was many, many centuries later that we got a computer machine. That was Charles Babbage in 1822. He invented the difference engine. It was a mechanical computer. And the first programmer of Babbage's machine was called Ada Lovelace. It was a lady. She wrote the first computer program. It was an algorithm. Shortly after that, a guy called Boole systematized logic. And that's why we often talk about Boolean logic. And that's really what computers use in order to be logical. We had the first motion picture camera in 1895, which launched the world of multimedia. And in 1947, the transistor was invented. More about the transistor later, because it's a key landmark in technology. We landed on the moon in 1969. Doesn't really relate to the web, but it's worth pointing it out. And in 1971, we got the first microcomputer. That was launched by Texas Instruments in the US. 1985, the introduction of Wi-Fi. And in 1989, Tim Berners-Lee invented the World Wide Web. Another key benchmark, of course, is the launch of the iPhone, the smartphone, in 2007. Then there's a gap. We've been waiting for all sorts of things, but I guess the big thing that we're waiting for is 2040, which is the estimated date that the singularity occurs in which technology achieves greater than human intelligence. Are we going to get there? Well, maybe this talk will give you some ideas. Beyond that, 2050, all bets are off. You're going to have to consult your system administrator. Okay, so let's kick off with logic. And who better to do that than Dr. Spock? What does Dr. Spock say? If you eliminate the impossible, whatever remains, however improbable, must be the truth. Well, let's look into logic in a little bit more detail. Aristotle, I mentioned him before, one of the great philosophers, 384 to 322 BC, invented or formalized logic, and he called it logos. He came up with the notion of the syllogism. It's a kind of logical argument that applies deductive reasoning to arrive at a conclusion based on two or more propositions that are asserted or assumed to be true. So, what does that really mean? Well, Lewis Carroll had a lot of fun with logic in his book Alice in Wonderland. Lewis Carroll, bear in mind, was a mathematician. So what was he doing? Here's a story about the pigeon from the book. You're a serpent, and there's no use denying it. I suppose you'll be telling me that you never tasted an egg, said the pigeon. This pigeon had just met Alice. I have tasted eggs, certainly, said Alice, who was a very truthful child. But little girls eat eggs quite as much as serpents do, you know. I don't believe it, said the pigeon, but if they do, why then, they're a kind of serpent. That's all I can say. So what's going on here? The pigeon asserts that little girls are some kind of serpent because both little girls and serpents eat eggs. It's entirely logical, but is it correct? This is how we actually set out the pigeon logic. It forms something called modus ponens, or affirming the antecedent. 3 stages. If little girls eat eggs, then they are a kind of serpent. If P, then Q. Alice, who is a little girl, eats eggs. P. Therefore, she is a kind of serpent. Therefore, Q. Why is the pigeon wrong? Well, an argument can be valid but have no bearing on whether statements in the argument are true. If today is Tuesday, then John will go to work. Today is Tuesday, therefore John will go to work. The argument is sound so long as the premise that John does work on Tuesdays is correct. If that isn't correct, then the argument doesn't work. Okay, so that's logic. Now, what about this thing called a transistor? It was invented in 1947. Most of you probably know that a transistor exists, but how many of you actually know what it is? Don't forget, it replaced something that was a little bit older, valves and relays, which are electrical or electromechanical. Well, a transistor is basically an on-off switch, and from that the computer is able to adapt and use the logic of Boole, Aristotle and the Babylonians. This is a circuit diagram showing the on-off switch of a transistor. Basically, a little bit of voltage is applied to turn a switch on and off. That's all it is. And that allows us to create a whole load of logic gates which are put into circuits to make the computer do all the clever things that we expect it to. The main switch is the NOT switch, the inverter, and that is used to build a whole load of other switches, an AND gate, an OR gate, NAND and NOR, and my personal favourite, something called an XOR. Here you can see on my slide what happens with all of these. Typically, 2 inputs, which are binary, 0s and 1s, create an output, also binary, 0s and 1s. The exception is the inverter, or the NOT, which basically just switches the input. So a 0 in is a 1 out. I like the XOR because when I started out in computer games programming years and years ago, and we're talking about early 80s, we used to have to program the graphics bit by bit, pixel by pixel on the screen. You probably think of these now as retro graphics. And one of the big problems was moving something like a Space Invader across the screen without actually deleting the background was quite tricky. The XOR let you do that. It would switch a pixel as you moved across, and then when the Space Invader moved on, the pixels were replaced. And here you can see Space Invaders doing just that. Some of the logic operators of those gates are reflected in these graphics. So you can see a little smiley face is getting mapped across a checkerboard, and the XOR gives you this interesting effect, but it does mean that if you map the face twice, the second time you map it, you restore the checkerboard to its original state. That means you can move the face on another little pixel. Okay, let's have a look at algorithms. And Dr. Spock, again, thinking logically is the key for this. An algorithm basically specifies a series of logical steps that perform a particular computational task. Algorithms were originally born as part of mathematics. The word algorithm comes from the Arabic writer Muhammad ibn Musa al-Kazami. And they're kind of like recipes. An algorithm tells you how to accomplish a task by performing a number of steps. An algorithm expects a defined set of inputs and produces a defined set of outputs. You'll be familiar with algorithms if you've done any programming or scripting, and this is just a little example. The problem is, given a list of positive numbers, return the largest number on the list. And you can write the algorithm by hand, which has been done here. 1, 2, 3. Set max to 0 for each number in the list. Compare it to max. If it's larger, then set the max to x. Max is now set to the largest number in the list. That's a kind of recipe. If you want to actually code that, it depends on the programming language that you choose. The example I've shown here is an implementation that is done in Python. Okay, let's talk about computers. Most computers follow this architecture. you've got a CPU, or the processor, which is on the right there, and you've got the program or the data on the left. And there's an address and data movement between those two. So the CPU can ask for data and it can store data. Very simple, very straightforward. In order to make this all happen smoothly, think of all those logic gates and chips that we just talked about, and think about timing. All of this has to happen in a particular order, and binary computers always have a clock that tick-tock sets the point at which the data can come and go. And exactly like the heart, the way the heart pumps blood around the body to keep us going, the clock on a computer allows us to do the calculations. The faster the clock, the faster the binary calculations. The computer architecture that I've just described is known as von Neumann architecture. It was originally described by the British computer scientist Alan Turing in 1936. Following that, we had the code-breaking Colossus in 1943 that helped us win the war against Germany. And John von Neumann in 1944 wrote a paper about a new computer design called EDVAC. In 1946, ENIAC was created, which was the first decimal computer using base 10. And in 1949, we had EDVAC, which was a binary computer. And that was actually operational until 1961. Here you can see Colossus, the first programmable electronic computer in the UK in 1943. Interestingly, in those days, most of the computer operators were female. Here you can see ENIAC in the USA. This was the first electronic general-purpose computer, 1946. And here you can see the way in which programs and data were entered into those kinds of computers. This is the punch card, which would get fed into a machine. What I remember as a young student, undergraduate student, is the VT100 video terminal. This is by DEC, and it was the first way in which you could really easily interact with a mainframe computer using the ASCII character set. So you could type in there and remotely control your computer. That was in 1978. My first job in the computer industry was with Cray Research, which was the manufacturer of the world's fastest computers. When I joined them, and we're talking about a long time ago now, 1988, they were selling this computer, the Cray XMP. It's pretty big, and if you bought it for $10 million, you got an engineer thrown in to keep it working. Now that computer was very fast in its day, but bear in mind that it is slower than the first generation Apple iPad. So things are going really fast, and processing speeds and capacity are still going up like crazy. So think about where we're going to be in 10 to 20 years' time. Okay, so let's talk about code in a little bit more detail. X equals x plus 1. Well, the first time I saw a piece of code was with a friend who was programming a Sinclair ZX80, and I was amazed to see him type in x equals x plus 1. I was quite good at maths, and I knew that that wasn't a valid formula. It was like x equals x, not x equals x plus 1. I soon got to grips with it, and that really began my lifelong love affair with coding. But back in the old days, we had some pretty basic technology to code with, and we also had some pretty slow processors. One of the first that I had to work with was the 68000, and we used to program this in something called assembly language, which is very low level, gets you very close to the binary and to the logic that we were talking about earlier. Here's the circuit diagram of the 68000 processing unit, and you'll see along the top banks of memory. Now pretty typically we'd be talking about 64K bytes of memory. That's absolutely tiny compared with contemporary computers. On the left-hand side, upper left, you can see the CPU, and there's a whole load of logic that is also stuck onto that circuit. Now, binary is pretty meaningless. It's not quite as meaningless as what we see in the matrix, but not far off. So computer scientists came up with the idea of hexadecimal as a way of looking at binary in a slightly more efficient way. And here's a hexadecimal dump of some code. Well, you can see it's still pretty incomprehensible. So when you're programming a chip at the low level, we came up with assembly language, and this is for the 68,000 chip, which powered a lot of computers certainly in the 80s. And you can see the commands, pretty basic, but they allowed you to do in combination all of the things that you needed for most calculations. This is an assembly language printout for the 68,000. And it's quite laborious. If you wanted to add two numbers together, you would have to get the numbers from memory, load them into something called the accumulator, add them together, store them back out into the accumulator. And most chips couldn't do multiplication. You had to shift binary left and right and do all sorts of clever tricks to get that kind of stuff to work. But over time, computer languages were developed to make it much more interesting and much quicker to code a computer. So you're very lucky these days if you're learning to code or write scripting, because we've had many decades in which languages have improved and become much more human readable. But we did have something called the Code Wars, and the question for me and to you is, did the bad guys win? The Code Wars really went on in the 80s. And there were two types of programming languages that had evolved. We had declarative programming languages, which described what a program should accomplish. And in a way, these languages were more like how we think. You can describe a problem, what you want to achieve. Isn't it great if your code then gives you the answer? Those languages, though, were pretty difficult to understand and pretty difficult to program. A great example was Prologue, and most of these languages were logical, expressed in terms of relations, and they were also self-modifying. So hold that thought, because we'll come back to self-modifying. Procedural programming languages, in contrast, described how a program should accomplish something, a series of computational steps to be carried out. So C++, JavaScript, etc. They're those sorts of languages. But imagine having to think like that. When we program, we have to decide what needs to be accomplished, but we also have to tell the code how to accomplish it. So in a sense, although the procedural programming languages dominate today's programming world, actually the declarative ones have perhaps more potential. And as we move towards smart coding and the world of AI, declarative programming is to some extent having a bit of a comeback. So there we are. That was the Code Wars. Declarative programming versus procedural. Procedural won for the time being. Let's think about this. The monkey and the banana problem. There's a monkey at the door into a room. In the middle of the room is a banana hanging from the ceiling. The monkey is hungry and wants to get the banana, but he cannot stretch high enough from the floor. At the window of the room, there's a box the monkey may use. So how do we solve that problem? Well, interestingly, a declarative language is really good at this. You describe the room, you describe the task, and the language will actually solve it. We've got a piece of code here. This is Prologue, and this is all that's needed. This will chug through the variations and eventually spit out the option that you need to achieve. So slightly strange to look at, but very efficient code. And you can see why the declarative languages lend themselves more towards smart coding. But what should you be programming? Well, I think the first thing to say is it's the programming environment that is important, more so even than the language in many cases. So iOS is a great programming environment. Scripting languages can generally be easier as well, as allow runtime changes. So scripting languages are run on the hoof. They're not compiled, they're not as fast typically as a programming language. Middleware such as Unity can make life even easier, especially if they're cross-platform. But watch out, license agreements for middleware aren't always that friendly unless it's open source. And there is a bit of an overhead that can come on. You can get the Winnebago effect, a lot of fat, slow code that you don't really need. And more on Winnebagos later. Mixing different language types is now very common. So for example, for the web, we mix JavaScript and PHP for mobile. Most languages ultimately are inspired by C or C++, which are now pretty dated, and they're verbose for non-maths applications. Interestingly, a lot of languages do compile to C or C++ before they get turned into machine language. The important thing to remember is that learning skills are transferable between languages, but I can say that you will never regret learning JavaScript. It has a momentum now across the planet which really is unstoppable.